in this question. What are the core rules of propositional logic? What is predicate logic? Let's take a look. So, logic in our code, and logic in general, I should say, this is more of a philosophical question than it is really a computer programming question, but you'll see the applications to computer programming in just a minute. Logic defines a set of rules that determines if things are valid or not. And we use logic so that we can all play by the same rules. If you're working in Python and somebody else is working in Python with a very different set of grammar rules, your code will not look the same. Consequently, if you're operating by different rules of logic, your code will not be the same. So we all need to operate under the same logical rules in order to express our ideas and communicate with each other. And so when we look into mathematics, we have various symbols that we can use to kind of define and communicate our logic. In Python, if we had two booleans, we would write P and Q for their conjunction, whereas discrete math, we would use this and operation, this and symbol. P or Q, we can do not P, which is called the negation. We can do not P or Q, which is an implication, and so on, so forth. We have many different ways of expressing logic. But what do these mean? Well, these are ways that we can express Boolean logic in our code as well as what they would mean. How do we simplify Boolean logic? Well, whenever you see the AND operation, right, we know that there's only one possible way for the result of an AND operation to be true. If we think of the possible inputs as P and Q, we know that this AND operation can take a left-hand side of false and a right-hand side of false. And if you're familiar with an AND in Python, you know that that outcome should be false. You also know that the only way that an AND operation or a conjunction should be true is if both of its inputs are true. And so we have various ways of demonstrating this within our code. Python gives us just a few ways of expressing this. We have and, we have or, as shown here. And or is always true except for when both of its inputs are false. We have negation. We can use not to invert the sign of a given input. However, what we don't have that's also commonly discussed in logic are implications, right? When P is true, right? This is almost always formatted in terms of a hypothesis and a conclusion. So if P is our hypothesis and Q is our conclusion, right? The only time that is true is if our hypothesis is true and our conclusion is then true, then that evaluates to true. However, if our hypothesis is true and our conclusion is not true, then the statement as a whole is invalidated because our hypothesis should have been true. Why was our conclusion false? That doesn't make any sense, and that's why we get this outcome of false. On the flip side, if our hypothesis wasn't true to begin with, then the result doesn't really matter, right? We have no way of negating, right, the truthfulness of the statement as a whole, and so we end up with a true statement because our hypothesis, our initial premise, just wasn't true to begin with. We also have things like bidirectional implications, but the applications of these to programming is not very elegant. And I say this because there is a reason that Python only has and or not. But one more thing that is very commonly found in other programming languages, just not Python, is the exclusive OR. We actually do have a bitwise operator for the exclusive OR in Python, but the essentially an exclusive OR is an OR statement, right? True or false or true evaluates to true. But the condition where both of our inputs are true, well, we don't want that. And so you can actually express this as P or Q and not P and Q, right? And so we eliminate that when both inputs are true, right? We end up with a false statement. But all of this talk of Boolean logic, where does this matter? Well, we have this idea of logical flag setting, right? If I wanted to write a function, and this is actually very common if you're writing interfaces for Python for lower level languages, in Python we typically won't use this type of flagging, But this is very common if you're writing, say, a C++ script or anything of the like. You'll use this type of these flags to indicate the operations that you want to be performed. And so if I have this simple calculator and I want to evaluate whether or not to sum my two inputs or to multiply my two inputs, well, I could wrap everything in this exclusive OR, right? And if I use an exclusive OR, what I'm doing is I'm verifying the user has either inputted one flag as only inputted one flag to be true, and so I know that's either sum or multiply. And so when I go to evaluate this, we see that it looks like my simple calculator is working, right? When I use the multiply flag, 2 and 4 multiply together. When I use the sum flag, 2 and 4 are summed together. But where this gets a little dicey is if I have invalid inputs, right? And I would typically raise some type of value error here, some type of error in a general sense here, but I'm simply returning incorrect input just so we can keep the program running and I can demonstrate the output. If I do not input a flag, this XOR, it returns false, which is what I want in the long run, right? But I just return this incorrect input, or I raise a value error of incorrect input. Same thing if I have two flags, right? If I didn't use XOR to test this, this would actually return the sum. And if I want the sum and the multiplication, why am I just getting the sum back? But since we are using this XOR, this exclusive OR, we return this incorrect input. But the only thing less helpful than an error message is a vague error message. I don't like this code necessarily, and what I would do is simply check if, right, my sum and my multiplier flags are true, right? And so let me comment this out. Then I would catch that error and I would return it early. I would say, well, both are true, right? And so we don't want both to be true because we can't perform both of these operations without refactoring the function as a whole. And I can use this idea of a NOR, right, which is when my sum and multiplier are both false, and I can return both false. In this case, I've caught the possibilities that I've inputted more than one flag, or I have not inputted any flags, and we can do away with this XOR because all of the other possibilities have been taken or have been accounted for, and I can use my calculator as expected, and now I have more meaningful errors or return values, something that conveys to the user that something went wrong, but here is what specifically went wrong. And so we always use logic in our programming to dictate the flow of what's happening and when it should happen. But where else do we encounter this type of logic? Well, one place I can show you is in the standard library. We actually see this fairly often. If you've ever used argparse, argument parser, or the Python standard library argparse, you have encountered this type of logic, this type of XOR exclusive group logic. If you've ever used add mutually exclusive group to control whether or not just one or multiple flags can be passed, you can actually see here that I can run this program from the command line. I can have it parse my arguments, and you'll see I end up with this namespace of x equals 2, y equals 10, right? And I pass those in here. And I passed a flag of sum equals true. I can additionally pass the flag here required equals true, and this guarantees that an input into one of these groups must be provided, right? I can't just tell the simple calculator to just run with two numbers and just give me back whatever. I have to tell it what operation to apply. And so you can do this within argparse. Now, if I want to actually run this simple calculator, I would actually end up calling vars on it, extract all the namespace as a dictionary, and then I would unpack that into my simple calculator function. This is one of the ways that you can call a function from a parsed argument, or from a namespace, I should say. But how does this work when I pass more than one flag? Well, I'm catching the error at the command line input now. I have this kind of logic repeated within my function and outside of my function, except I'm letting my command line's input checker, if I'm running this from the command line or the terminal, to catch it for me. And so I'm able to pass in two flags, and argparse correctly detects, right, that you cannot use two of these flags. And this remains true even if I use multiple flags. I don't get the most helpful error. I get mul is not allowed with sum. I wish it told me that mul was not allowed with and then list enumerate all the options, but argparse is actually a very flexible library. You can pass in custom help and custom error messages as well. But you can see here that this logic already exists within the framework of Python's built-in library, and so we don't need to repeat it unless we're intending for our users to use this as well. However, I do want to share with you a way that we can simplify some of this logic. Booleans are not just true and false. In Python, Booleans inherit from the integer. And so this means that false is the equivalent of 0 and true is the equivalent of 1. If we have 4 of these flags and we want to ensure that at least just 1 is passed, we can simply take the sum of all of those flags. If the sum of those flags is 0, we can say no operator flag was specified. You need to specify at most 1. However, if the sum is greater than 1, we can say, well, you specified sum and you specified subtract. That doesn't mean anything to this program. Please reevaluate your output and make sure you're only setting 1 flag. And then we can go ahead and perform our operation. Now that we have moved all of this error checking to the top of our function so that we're able to fail fast and we're able to fail logically. But where else might this logic matter? How else can we define this logic? We've seen it as Booleans, we just represent it as integers. How else can we pass logic into our programs? Well, there's very simple things called rule engines. And this is almost like a class-based approach to performing some type of checking or some type of what we call business logic. And so if I have this evaluation class that returns the result or provides a scaffolding for a result, I can actually perform quite complex operations. If I have credit cards to match against, and if you just Google credit card regular expressions, you will come over a fantastic Stack Overflow answer that has many different credit cards as well as regular expressions that provide whether or not they match a given input. But you can actually pass in this logic as data structures. And this is different than what we've shown before, because before our logic was supplied as code, not as data structures. And so what we're able to do here is we're able to iterate over all of the rules that we have defined, right? And our rules are simply that Amex matches this pattern, Visa matches this pattern, your BC Global card matches this regular expression pattern, and we can evaluate them. And we can return something meaningful to that evaluation so we can check, right, if it matched, if that result is not none, we simply print. And if I were to gain a new card, I don't need to go into my code base and add a new branching conditional. I don't need to add, well, elif, right, matches this regular expression, print MasterCard. I can simply update my data table, update wherever these rules live, and you can think of these as a very simple table format. If you're working in a database, I just need one row, append another row that has a MasterCard along with a specific expression, and my code base does not need to change. I just need to update my database. And this is fantastic if you're performing things like analytics, if you're a data analyst, because you don't need to make any pushes, make any commits to any code repository that the software engineers are hogging over and don't ever let you touch. You can simply, you can update a data table, you can pull that data table, you can append it yourself, and then you can run the evaluative logic on it from the software development side without needing to make any changes to the code base yourself. But that's not even the best part of this type of business logic, of these type of using rules instead of control flow. The neatest part, in my opinion, is inference. We have two types of inference. I'm going to share with you forward chaining inference. There's also backward chaining inference. But what makes forward chaining inference so cool is that if we have a limited set of facts, say if we know that a duck is a vertebrate and a duck also flies, and we know that a cat is a mammal, what other facts can we infer if we also have a set of rules? So if these are our facts here, and we have this set of rules, If the animal is a mammal, well, that animal is also a vertebrate. If the animal is a vertebrate, well, then it's also an animal. If we have a vertebrate that also flies, well, it has to be a bird. And so when we go through, if I were to run this, we can see that I start off with just these few facts. I start off with duck is a vertebrate, a duck flies, a cat is a mammal, and I end up with these set of facts. I've taken facts, I've applied a set of rules, and I've inferred new facts from it. This is the beginning of machine learning. This is what we call machine learning way back in the day. Not true machine learning because we're not updating based on errors. However, we are making inference based on logic. And so, I know that a cat is a mammal, therefore I know that a cat's also an animal. This is an inferred fact. It wasn't in my original facts table. And again, these data are stored as such. They are data. I do not need to make any changes to my code to add a new fact in. And so, if I wanted to say, well, I want to classify a dog. I know that a dog is a mammal. Well, let's update my computed facts based on the existing rules that I have. Dog is also an animal. If it's a mammal, it's an animal. And so you're able to make inferences about unseen or unknown facts based on this set of rules. And what's fantastic about this set of rules is you can go ahead, you can subset it. Given what I know about ducks and what I'm able to infer about ducks, go ahead, tell me everything we could possibly know within this system about ducks. Well, a duck's an animal, it's a bird, it flies, and it's a vertebrate. How this works a little under the hood, I just want to share with you. We essentially have this outer while loop that is telling us if we're updating our facts base or not. We create an empty set of new facts to add into our original fact set, and we essentially say, after doing some type of inference process, we say, if our new facts are a subset of our existing facts, we've added nothing new to what we know, and so we're not able to infer anymore, so let's kill this loop. But if we are still learning, if we are still making new facts, let's add those new facts to our existing fact kind of database, and you can see here that this loop spins twice, this while loop spins twice. I originally learned, in my first iteration, I learned that a duck is an animal, I learned that a dog is a vertebrate, and I learned that a cat is a vertebrate as well. Then, in my second pass-through of this logic, I also pieced together that a dog is an animal and a cat is an animal. And the reason we need two spins on this is because the order of our logic here, right, the vertebrate to animal comes after the vertebrate to mammal pairing. And so we need to just pass through this series of if statements just one more time to make sure that we're able to infer everything we can. And then once we have, we kill that loop and we present all of the facts that we have found. And so that's the ins and outs of forward chaining in terms of inferencing and business logic. And so we're able to apply logic in various ways. It doesn't need to just be code. Logic is not if-else necessarily. Logic can be represented in data structures and facts, separated into facts and rules, and you can make inferences on it and learn something new.